So cotangent and tangent, if you're, I don't know if any of you guys have referenced the book at all, not necessarily, I know, but they are in lesson 4.5 along with secant and cosecant. Okay, so just kind of an FYI there if you're looking for them in the book. Tangent, cotangent. While some things stay the same, some things change. So definitely some similarities, definitely some differences. As we look at tangent, okay, one of the big first things I need to mention is that the period of a tangent curve has a length of pi. In comparison to what was the length of a typical period of cosine or sine? That was 2 pi. Okay, so sine, cosine, secant, cosecant all have a length of 2 pi. Tangent and cotangent are going to have a length of 1 pi. Now, with that in mind, what I'll end up doing is when I ask you guys to do your homework, my minimum expectation is going to be that you do 2 curves or 2 cycles, because here's the deal. What you're looking at right in here for tangent, this is 2 cycles. Okay, and that's what I want to be able to make sure you have everything going right. With the idea of tangent, the first thing you do on tangent is that before any phase shift or anything, the origin has a dot at it. That's where there's an intersection point on the origin is at tangent. Now, you'll notice I said a period is pi, yes? So you'll notice from 1, 0, one intersection point, to the next intersection point is a distance of pi. Or we can also look at asymptotes, okay? Here we have an asymptote of negative pi over 2, and an asymptote of pi over 2. The distance between negative pi over 2 and pi over 2 is pi, which is the length of a period. So one period is one curve, whether you think about it going from asymptote to asymptote or point to point. Okay? And then the key to know about tangent is that tangent starts with a point or a 0 on the origin.
No matter
okay?
Where, no matter like what.
Well, before any phase shift or anything.
So it starts with what?
Okay? So yeah. Now, with this in mind, you'll notice that tangent is an increasing curve. It reminds me a lot of y equals x cubed, yes? Okay. A couple of things about tangent. First of all, what is tangent as a fraction?
Opposite
Y
over
over X.
Oh,
Okay.
sorry.
Nope, no. They're both good answers.
Sine.
It is opposite over adjacent, which is going to lead me to saying it is y over x,
Or sine over.
which y over x is equivalent to saying sine x over cosine x. All good answers, and because I wanted to go through them all, and I wanted the lead here. Now, we haven't really talked about tangent being sine over cosine a whole lot yet. Yet being the key word, because that's a big chapter 5 thing. You'll know that in chapter 5, okay? But what I'm trying to point out a connection here. Our tangent graph relates to the sine and cosine graphs, okay? If you think about cosine, what does cosine do here? Cosine starts where? At 0, and then what to do? It goes up, and then it comes back down, and where does it have its next 0? At pi. And then it goes down, it comes back up, and then it has a 0 at
That would be
2 pi. That's what I said,
so
isn't it?
That's
Oh.
why cosine is
Hold on.
period is 2 pi.
Hold on. Okay, I'm talking about sine right now. I'm not sure what I said. Only the recording could tell me. Okay? But the idea here is that sine is on top, and that's the connection I'm trying to make first of all. And that is that here, sine would start at 0. Repeat this, I'm not sure what I said. And then it would go up, right? And then next time it crosses 0 is at pi. And then it goes down, the next time it crosses 0 is at 2 pi, right? Notice those zeros are matching up with the zeros of tangent, right? Okay, the reasoning is sine is in the numerator. What happens when the numerator of a fraction is 0? That fraction is 0, right? So the idea here is that any zeros for sine are automatically going to be zeros for tangent. So sine x zeros are going to be tangent zeros. Maybe I should say tan x zeros. Now, on the flip side, we have cosine in the denominator. What happens when a denominator is 0?
It's undefined.
That fraction is undefined. What does that equivalent to in my graph here? Undefined part of the fraction, or part of the graph is our asymptotes. Okay, think about cosine. Cosine starts high, and then what's it do? It goes down and it crosses, and then it goes down, has a minimum, and then it crosses, and it has a max. Notice what's happening. The places it crosses the x-axis are actually asymptotes. And that's because when your denominator is 0, that makes your fraction undefined, and asymptotes. So any place that cosine has a 0, those are going to be asymptotes for tangent. It's going to be tan x asymptotes. Now, is that necessary knowledge you have to have? No. But it's a connection that can be made of, okay, how does our tangent graph compare to our sine and cosine graph? Because tangent is sine divided by cosine. What?
It has me be.
Okay, well, right now I'm just trying to share some information. We'll get to the graphs, okay? Just give me time, I'll get there. Now, cotangent has similar information. And with cotangent, notice it says here the first thing you'll draw is the asymptote on the y-axis. So, guess what the period length still is? Period length is still pi. Okay, so tangent, cotangent, they have the same period length. We're not going to get too confusing there. So they both have the period length of pi. But the difference here, with tangent, I said, okay, the first thing you do is you put a dot at the origin. With cotangent, the first thing you do is you're going to have an asymptote at the origin. So an asymptote on the y-axis. And then if the length is period, how often do we have asymptotes? Every pi. So if there's an asymptote at 0, there's an asymptote at pi. There's an asymptote at 2 pi. Now, what's in the middle of the asymptotes? The halfway points are your points, your zeros. Up here it was reversed, right? Up here the halfway points were the asymptotes. Okay, so it's just a matter of knowing what do we have to start with, where. Okay, so knowing, okay, it's tangent, I start with a point, and that's what I'm doing. Cotangent, we're going to start with an asymptote, and that's what we're moving around. Okay? Now, while we're here, oh, and the other thing to notice about cotangent, and instead of it being an increasing curve, it is a decreasing curve. What do you think cotangent is as a fraction? Because tangent and cotangent are reciprocals. So if tangent was sine over cosine, cotangent is cosine x over sine x. Now, can we make the same connections as earlier?
Yes, but opposite, right?
Yeah, but opposite, right? Because if cosine is on top, any place cosine equals 0, cotangent is going to equal 0. Well, remember what's cotangent do? It starts up top, it crosses, goes down low, and it crosses and goes up high. So cosine zeros are matching up with cotangent zeros. So cosine zeros match up with cotangent zeros. And what do you guess about sine in the denominator? Any place sine is 0, we're going to have asymptotes, right? Right there at 0, pi, and 2 pi. So sine zeros create cotangent asymptotes. And again, this is not necessary knowledge to be able to graph these, but it's trying to make connections.
It might make more sense to do a graph.
Exactly. Exactly.
Yeah.
Okay, now you have a chart of information here, yes?
Yep.
Similar to our previous charts, but yet different.
So just
We still have the ABCD, right? A, we're not going to use the word amplitude here because we don't really have an amplitude with tangent, cotangent. A value, which is, this is what amplitude is doing, is going to be how far do we stretch, vertically stretch, or instead of saying the word compress, it says flatten. Okay, now that will just make a difference of how the angle I go through the origin at, and I'll explain that. I'll show some examples. Okay, I'll explain that in directions. But if your A value is bigger than 1, we're going to stretch it up. It's going to be taller. If our A value is less than 1, we're going to squish it down. We're going to flatten it. Okay? If A is negative, it's still going to be a reflection. Now, what's a reflection going to do? For instance, tangent that was increasing, if you reflect it, it's now going to be,
Okay.
it's going to be decreasing. It's going to look like a cotangent curve, but still have a tangent location. Okay? Big change. Here's one of the biggest things. What about our period?
It's a pi divided by 2.
And why is it pi divided by b instead of 2 pi divided by b?
Because the period is 1.
Our period is only 1 pi this time. So it's equivalent, right? But our period was only 1 pi, so we're going to do 1 pi divided by b. Phase shift is still c over b. Center line is still d. Okay?
Let's try this.
Ready to try it?
I think.
Okay, well.
And we don't do amplitude anymore, it just equals A.
It's our how we're going to stretch or flatten. And I will demonstrate to show you the difference of what I'm expecting about something that is stretched versus flattened.
So if we were to get A equals 3 stretched.
Right. But I will, and I'll show you how to graph that. Okay, here we go. Examples. I'm still going to go through, and we're still going to go through all the, I won't say all the same questions, all the similar questions. How's that?
Practice of finding the...
Yeah. So what do we know?
Tangent.
Okay, this is a tangent curve. Now, tangent curve, one thing I want you to think, is this increasing or decreasing?
Increase.
So this is going to be an increasing curve like that, right? Unless, of course, there's a reflection. And I usually do this later, but you will have to think about, are we starting with a point or an asymptote? Okay. What's my center line?
-1.
Instead of amplitude, I'm going to ask, are we stretching or flattening?
Stretching.
We're going to vertically stretch by a factor of 2. And so I'm writing V point, period, and then stretch. And it's vertical stretch by a factor of 2. The key there is to know vertical stretch. What about a period?
5/6.
In order to do the period, we do pi divided by b. B is just 6, so pi divided by 6. And
Phase shift, -5/6.
the question was going to be, is there a phase shift?
Yes.
And that is still c over b, offset that middle sign. So this is going to be a negative pi over 6, which is going to take me which direction? Left.
Stop, I literally wrote it.
Okay. We're good with the information then, right? That's the basic easy part we've been doing. Now, one of the easiest things to forget, center line, label it.
-1.
Whether you label it out here or whether you label it in there.
I make me think about my homework. Yeah.
Well, and here's the reason it's so easy to forget, I feel like, because I don't have an amplitude I need to label.
I think
We're not going to label anything with our stretch. So I feel like for me, that's why I forget to label my center line so easily. So you'll catch me on it before we're done with all of this, guaranteed, because I forget. Just like I would occasionally forget, I would jump right to the horizontal,
Yeah.
and I'd forget the vertical labeling, because the horizontal is the necessity.
Yeah.
Okay. Now, I believe I mentioned, when we draw this, I'm going to have minimum requirement of 2 cycles. Okay? Now, this stuff gets real easy to do more than the minimum. Okay? Just because of how it's designed. Now, our period is pi over 6, correct?
Mm-hmm.
So we need to label some pi over 6s. Minimum, I would say 2 to 3, depending on how it ends up, how we end up going. So, I would say minimum two of them. Now, with that in mind, I'm not going to make them real tiny because otherwise they'll get real tedious to get our graph in. So I'm going to do a pi over 6. And then I'm going to do another one that is 2 pi over 6. But really, what is 2 pi over 6? Pi over 3, yes? Now, we also have to have a phase shift.
Let's go left.
Left pi over 6. So what also should I do? An equivalent mark to the left that is at negative pi over 6. Okay. Now, with that in mind, each pi over 6 represents one period, yes?
Yes.
What I need here is I need you to take each period and divide it in halves. We don't need fourths today. Each period gets divided in halves. So what's that mean I need to do here?
The tick marks.
Tick mark, tick mark, tick mark. Now, I don't necessarily label them, but what is a half of a sixth?
A 12.
A 12, because 1/2 times 1/6 is 1/12. So if you labeled these, you would be working in twelfths. Okay? Now, keep in mind, it should make sense. This is 1/12. This is going to be 2/12. This would be 3/12, or 1/4. This would be 4/12, 1/3, right? It makes sense.
Yes.
Okay, not required though. Now, with that in mind, we're about ready to draw our curve. Is this tangent or cotangent?
Tangent.
This is tangent. Now, what does tangent say we start with?
Origin.
You have a dot on the origin. Now, okay, I'm not actually putting the dot here right now. I'm just thinking. I would have a dot on the origin, but this is where I'm not going to draw the original because it gets way too confusing. A dot on the origin, but then we have to phase shift it. Where am I phase shifting this dot?
Pi over 6.
So right there, there is the equivalent to me putting a dot on the origin. Okay? Now, once every period, I will need a dot or a point. So where is another point I can put? Does it actually work out to be the origin?
Yes.
Now realize it won't always, right? It's that whole, just depends how it overlaps, right? But here's the deal. Every pi over 6, so there's actually a point on the origin. Where would be another point? Pi over 6 and 2 pi over 6, which is pi over 3. That's having a point every origin. So I actually, with not even trying to, I just set us up to where we could draw 4 curves. Okay? That wasn't my intention necessarily. It's just so easy to do that way. Okay? Now, once every cycle, you have a point. What's in between the points? Asymptotes.
Yes.
So your halfway points are your asymptotes. So where do I have asymptotes?
Negative pi over 12.
Right there, in between. So negative pi over 12,
Pi over 12.
pi over 12,
Is that 3 pi over 12?
it would be 3 pi over 12, so pi over 4. I just didn't get it labeled.
I would say my least favorite part about these lessons is the dotted lines. Because on the homework we had to draw something.
Dotted lines, they look cool.
Wait,
Okay.
Why are the asymptotes there? Like at the halfway point?
Because a cycle goes from either point to point or asymptote to asymptote. The opposite is in the midpoint zone. So we start off by drawing our points. Halfway in between every set of points is going to be your asymptotes. Okay?
And then like the opposite would be your point.
Just hold on. Let's just finish this right now. Okay. Now, this is a tangent curve, so increasing or decreasing?
Increase.
Increasing. And this is a stretch or a flatten?
Stretch.
A stretch. And I'll compare later with a flatten. But so I'm going to, technically I need to start over here, but I'm going to start right here for right now. I'm going to draw an increasing curve that looks something like that. The key, this is a stretch because it doesn't really flatten out much along the x-axis. It kind of keeps going pretty vertically. Now that's one. Technically, I really should have this one over here, shouldn't I? Because we put a point here. So I really should have this one over here. Draw appropriately, pretend the next asymptote is there, right?
Can we extend the graph and just put it there?
You can put an asymptote. Yeah, you could do another tick mark and put the asymptote there, most definitely. And in fact, that's what I would probably do. I just didn't here. Now, this, even though I have the extra information, this is minimum requirement. However, I feel weird having the asymptotes and the points and not drawing more tangent curves. So that's why I'm saying minimum is 2, but in this case, it is so easy to get extra, isn't it? And you may realize after you get into it, you may draw less points, less asymptotes, whatever. But okay, can we get one more example in?
Yes. Let's hope.
I want to because we're going to be missing 2 tomorrow. Okay, so I want to talk about some more. So let's go with this next one. Okay.
Vertically flattened by -1. I forget, by a factor of negative. Is that what you said?
Yeah.
Factor.
Yeah, by factor 1/2 and reflected.
Center of 3, though.
Or by, yeah.
Yeah, center of 3, reflected, and flat by.
Center of 3, flattened by 1/2, and then reflected.
Okay, I'm agreeing with all this information. Center line of 3. This is a vertically flattened because 1/2 is a number less than 1. Notice I did not say negative because the negative is the reflect. Okay.
Periods 2.
Period is what?
2 pi.
Because
Divide
Pi
by
over
1/2.
1.
pi divided by the b value of 1/2 and pi divided by 1/2 is pi times the reciprocal 2/1, which is indeed 2 pi.
They shift positive pi over 2.
Agreed. Which means to the right.
Okay, phase shift, c over b, opposite the sign, so pi over 4 divided by 1/2, which is going to be pi over 4 multiplied by the reciprocal, pi over 4 times 2/1, which is 2 pi over 4, or pi over 2.
It increases.
Okay, and we kind of skipped over the detail, which is fine. You just have to answer it sometime. It's a cotangent curve. Officially, a cotangent curve is a decreasing curve. However,
With the
a reflected cotangent curve is actually going to look like a tangent curve. However, we still use the cotangent rules to set ourselves up here. Okay?
3 parts of 3.
Now, I'm going to label my center line as 3. Now, my period is 2 pi, correct?
Yes.
But I'm going to require you to do 2 cycles. So we probably should label out to 4 pi. Plus we have a phase shift right, so allow a little extra room. There's 4 pi, yes?
Yes.
In the middle of 4 pi is 2 pi. 0 to 2 pi represents a cycle, yes?
Yes.
Now, that's one cycle. What did I say you need to break a cycle into? Half. So 2 sections. So that means I need to label my midpoints, which my midpoints happen to be
Pi and 3.
pi and 3 pi. Now, here's the catch with this one.
With the little 2.
But we have a phase shift of pi over 2. Where's pi over 2?
In between 0.
In between all of those things?
Yeah, so we just need.
Yeah, so you need tick marks in between all of these because of our phase shift.
But do all of them have to be labeled?
No, they do not all have to be labeled. I labeled the first just to show what it is. I'm going to label the last. 4.5 pi is going to be 9 pi over 2. Okay, Now, what are we graphing here? We're graphing a cotangent. What does cotangent start with at the origin? An asymptote. So cotangent is an asymptote. But I'm not drawing it in yet because I'm going to phase shift it. Where am I phase shifting that asymptote? Pi over 2. So what I can put down for sure is that I have an asymptote at pi over 2. How often do I need asymptotes? Once a cycle. What is my cycle here? 2 pi. So if you notice, this one's right after 0. You need one right after 2 pi. That one's right after 2 pi. You need one right after 4 pi. Is that making sense?
Yes.
And then the middle of those sections are your points.
Also at the the little thing on the pi.
So you're going to have one at 1.5 pi and at 3.5 pi. Cotangent is decreasing, but reflected, so I'm increasing. And I'm going to flatten. So let me demonstrate a flatten. Notice what I did near the x-axis. It flattens, right? It's more horizontal, less vertical. Okay? Okay, get what you need. I'll hand you a worksheet on the way out, just in case you're not in here tomorrow. And then I can do the other 2 examples for those of you that are in here. Those of you that aren't in here, hopefully I got you some information. Homework is due on Monday? Homework is due on Monday. Okay. Yes. Whoops.
Oh, got it.
And I only pushed through that last example for the benefit of tomorrow.